We come to finally the all-important topic of derivation of Navier-Stokes equation, which is of extreme importance as far as Newtonian or non-Newtonian fluid dynamical motion is concerned. And if we are to describe the fluid motion by solving differential equation, Navier and Stokes are two scientists who developed these equations first independently. Navier is a French scientist and Stokes was British, but their work was done independently. But the equations are of immense importance and are kind of central focus as far as fluid motion is concerned, and we need to look at the behavior of fluid motion, and for that we try to solve Navier-Stokes equation. As we will see later, the Navier-Stokes equation turned out to be nonlinear, therefore very difficult to solve, and we will see why. So now we consider these equations. We have considering along the way different conditions, different motion, kinematic motion, equation of momentum, Cauchy's equation, etc., etc. But the main important equations that govern the fluid motion are Navier-Stokes equation, and therefore their solution for the relevant fluid flow that we are considering or we would be considering at times from time to time will reflect the solution of these equations for that particular fluid flow motion. We derived Cauchy's equation in three different ways, and it was good to see that we arrive at the same result. But for practical purposes, they are not of much utility. The reason being that it contains 6 stress tensors, 6 of them. Altogether there are 9. But it contains 6 components that are independent and by symmetry. It has pressure components also. So 3 pressure components and plus the Navier-Stokes component. So we have the density, we have the velocity components u, v, w, and we have the 6 stress tensor components sigma xx, sigma xy, sigma xz, sigma yy, sigma zz. So altogether 10 components. But we have only 4 equations to solve, and this is the problem. So since there are 4 equations to solve, that gives us for velocity, and that includes pressure as well as rho. So how do we come around this? So that is why we need to derive these Navier-Stokes equation so that we can somehow try to solve them. For this, what we do is that the stress tensor component, 9 components of stress tensor, we separate them into pressure and the other deformation forces that are acting, so which are stresses or viscous stresses acting inversely on the fluid motion when the fluid is deformed and the viscous fluid. Therefore, these forces develop, that is all these sigmas that I have just mentioned to you. If the fluid is at rest and we want to separate the tensor forces, then the 9 tensor forces at rest will be equivalent to only the pressure components acting on this in x, y, and z direction inversely. So if it acts, see, the only forces that act on a fluid at rest is the pressure, and if we are considering an infinitesimal volume of fluid arbitrarily within the fluid, then as we have shown in the diagrams also, then the only forces are just the pressure that is acting at the x direction face of the cube the y direction face of the cube, the x direction face of the cube is this, y direction is this, and the z1 is this. And the other forces, the sigmas appearing here, 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 and so on, they are 0. But this is for fluid when fluid is at rest. So remember, when we are making these assumptions or putting these conditions, then whatever we are saying is valid only when that condition is fulfilled. So at a fluid that is at rest, we have the three forces that are acting here, and so the stress forces reduce to these three components, only the pressure acting inwardly. Now that is why, since they are acting inwardly, but when we take the Cartesian coordinates x, y, z, we take the positive direction in the outward directions. So they are normally taken as this. So this is taken from origin, this is taken as positive direction. But if something is moving in this direction or a force is acting in this direction, a negative sign will appear. And the same is the position at other places also. So in general, the stress forces can be written, all their 9 components, as the pressure forces, the 3 components of pressure forces when it is at rest, and the strain forces or stress tensor, that is, if the fluid is moving, then the other forces can be written in the form tau xx, tau xy, tau xz, and so on. So you can see that generally this is denoted by tau ij, and this has been added to the pressure forces. So this will be the totality of stress forces given by pressure plus strain. This is also known as shear strain. So these are the total, because viscosity introduces stress and shear strain components, and these are the components that occur in totality, and they are the ones that complicate the Navier-Stokes equation or even the Cauchy's equation and makes it difficult to solve all the problems. However, when we are analyzing a problem, when we are analyzing a fluid flow motion, we have to determine them under the prevailing conditions of a particular problem. And you can see, well, this is a diagram only reflecting the pressure forces acting when the fluid is at rest. Then the pressure is acting on the x, y, and z cubical faces inversely. And since it is acting inversely, therefore a negative sign appears when we show the term of pressure that is being applied. So at fluid at rest, the total pressure that is being exerted on the fluid is known as mechanical pressure and is given equal to 1/3 of sigma xx plus sigma yy plus sigma zz, where sigma denotes the stress components in the relevant directions. And in this case, as I have explained, that this is the stress that is being exerted on the fluid inversely on a small cubical motion. So in a normal direction, which is the standard form. And because it is acting inwards, you see a minus sign there. And this term is used as mechanical pressure. So you see the sign as subscript M there with the P. And mechanical pressure is the mean normal stress acting inwardly on the fluid motion for fluid that is at rest.